So this is the main topic about the main thing about digital human control. Maybe I can go back into a short demonstration in order to illustrate again this this control with our own software. So we'll go back to the here it is. I will go back to preparation in order to define my digital human model. Okay, I will keep this morphology. Okay, and here, okay, so I move in position, I move in rotation here, give some input. So here what you can see is that I really move my digital human model in a physics way. It's not pure animation. It means that you can actually see it as if there were invisible springs and dampers between the red cubes and the virtual mannequin. And that's what you see here. If I move here, then the mannequin will try to find the most suitable position and posture, even if it's not reachable. So here, what you can imagine is that you have invisible springs between the red cubes and the corresponding bone it controls. And it's the same for the arm here, and it would be the same for the legs. I can move them in space, and of course here I'm moving them by hand with the mouse, but you have to understand that all this is real time, and the red cubes, they could be provided by actually motion capture software, okay, and moved by motion capture sensors, for example, okay. Can move the whole avatar in space if I want, but we really have a physics way of controlling them. And what you can see is that here I move them in position, but I can also define them to move them in rotation only, okay? Here it is. So I hope it's clear for everyone. Here we have a way of having a digital human model, okay? And we know how to control it in space in order to reach some targets. And now the next step of the training session is about ergonomics evaluation. So I will now show you how we can perform an ergonomics evaluation based on this digital human model and based on this current posture. So let's go back to the presentation. Okay. Here it is. So ergonomics evaluation. First, some words about the distinction between physical ergonomics and cognitive ergonomics. There are two main fields when we talk about ergonomics. Physical ergonomics is mostly focused on injury prevention, and it will provide some design and evaluation of workplaces so that you can reduce these injuries. It's mostly focused on postures, manual tasks, repetitive movements. You can see some example here, like you have a bad physical ergonomics here when you sit at your desk, rather than the right part is less prone to musculoskeletal disorders. Okay. Another example is this one. When you want to load, to carry a load, it's better to bend your knees in order to catch the load rather than bending your back. Okay. So additionally to physical ergonomics, you have the cognitive ergonomics, and this mainly focus on how well the use of product matches the cognitive capabilities of users. So it's mainly related to the mind and to the cognitive load of users, especially when you have to remember plenty of activities to do, or when you use a 2D interface that is complex, then it will increase your mental workload. This is linked to cognitive ergonomics. In this training session, I will not focus on cognitive ergonomics, okay? I will only focus on physical ergonomics by using this digital human model and motion capture. So physical ergonomics, the aim is to focus on specific work activities and to give recommendations in order to reduce musculoskeletal disorders. So it can give some recommendation on joint angles, joint efforts, repetitiveness, muscular fatigue, workplace environment. Here I give you some details. For example, when you sit at your desk, then it's better to be really seated straight with specific angles for the arms, specific angle for the lumbar spine. When you carry a load, it's better to bend the knees rather than bending the trunk. And when you also stand at your desk, it's better to be really straight and not bending the neck. So there are plenty of recommendations. They all depend on the workplace activities you perform. And it's mainly, it can be focused on mainly many parameters, angles, efforts, fatigue. Here is an interesting chart that I got from this reference here. The most important thing to understand is that depending on the ergonomics evaluation you want to perform, you will use different digital human models. And here you have the three different types of digital human model that we saw earlier. So the three here is mostly posture related modeling. So it's mostly based on the skeleton. Here you have some also a skeleton, but with torque modeling. So you can model the torques on the human joints. And at the end, you go to the musculoskeletal modeling. So you don't only have the skeleton, you also have the muscles modeled inside your digital human. And depending on the precision and on the ergonomics evaluation you want to do, you can use different kinds of digital human models. The most commonly used, they are only posture related, meaning that you will give recommendations on the joint angles. Like for the elbow, you would need, you would say that you don't want the elbow to be above 90 degrees, for example, and it will give you a score. We will see it later. You can also define some external forces on this digital human model so that in the end it will give you recommendation on the joint torques that you can apply, and at the end you can also give recommendation on muscle forces if you want to give really detailed evaluation. Okay. First we will focus here mainly on posture related models and posture related evaluation. I'm sure most of you know about some standard ergonomics grids and rules that exist in the industry. The most well-known is the ruler and Reba grids. That's what is displayed here. So this grid, they provide you some recommendations about what should be the joint angles to have in order to have ergonomics acceptable workstation. And here I give the example on the shoulder, for example. on the shoulder, if you are between -20 and 20 degrees, then it's okay. If your arm is above -20 degrees, then it starts to be complicated. If your arm is between 20 degrees and 45 degrees, then it's also complicated. If it's between 45 degrees and 90 degrees, then you get a higher score, and it's even more complicated and more risky if your arm is above 90 degrees. So this is an example for the human shoulder, but actually this standard, and especially ruler, they give you like thresholds on the joint angles for each body part. So for the shoulder, for the elbow, for the wrist, for the trunk, for the neck, uh, etc. And at the end, when you fill this grid, at the end you get a global score, ranging from 1 to 8, 9, it depends. But if the final score is between 1 and 2, it means that there is a negligible risk of getting an injury. If the final score is between 3 and 4, then it's a low risk, but it's better if you change the workstation. If the score is between 5 and 6, then the risk is medium. You need to further investigate, and you should change the workstation in a short-term delay. And the final score above 6, it's a very high risk. You should change your workstation right now, or you should change your posture right now, okay? So this is the example of the ruler standard. It's mostly based for the use for the upper body. You have the REBA. REBA is also used for the legs. And you have also other standards such as the OWAS or NIOSH grids. And they provide you with scores about the posture you should get. You can also add some parameters about the loads and the repetition of actions, but they are mainly just check boxes that you check, and it will also increase the final score. But there is no real recommendation on loads. These standards are really easy to use and to implement, but they are mostly used for postural risks. They do not really provide precise efforts criteria, and they do not always adapt well to specific use cases. What I want to what I mean is that mostly in the industry, specific industry partners will get inspired by this grid, but they will adapt it and invent new grids that are really dedicated to their own use and to their own workstation and to their own field of study, okay? So these are only standards to give some general scores. Historically, this ergonomics evaluation has been performed manually by watching videos. So you would have the ergonomists go on site, observe the operators, and capture some video. And in the end, they would analyze the video, make some annotations, measure the body angulations, and perform a manual analysis based on these videos. And what is important to know is that nowadays, thanks to motion capture tools and motion capture software, you can get this analysis automatically because you have the motion capture data, and then you apply the standards, the postural scores. You can compute them automatically based on the motion capture data. So there are some examples of this software, like the XR software. This is the one I'm showing you during this training session. You also have the NAO software, the Chimera software, the TEA Captive, and so on. You have plenty of them that can do this kind of analysis. Compared to manually done analysis, what is really important to understand is it can provide you automatic analysis. It can also give you some objective data, because the motion capture gives you objective data. It's not based on observation by a person. It's really based on the motion capture sensors. And it's also really a gain in time, because you can perform this automatically, and get analysis really easily and in a really short amount of time compared to manual labeling and analysis. Here I give you some examples on the XREGO software that we develop at CEA with a ruler analysis on a specific workstation. Since we also have the angulations on the human body, we can also have a simplified posture classifier. Here it's based on the decision tree, but based on the posture you have, you can have some snapshots here showing you that you are in a standing posture, you have the arms straight in the air, or that you are bending. Okay, so you can have some more high-level analysis also. And here is a video about a use case that we did in 2022. It was actually used for cobotics risk assessment, but we also do an ergonomics analysis that you see in real time here by different colors. The different colors, they represent the ruler scores on the human body. You can display them on a small interface here. The different scores between 1 to 6 or 8. You can pause the human capture, and you can add some loads, some muscular fatigue, in order to use the ruler analysis. Okay. So this was posture-related analysis. Now I would like to focus on efforts analysis. This is something that is not really handled by standard ergonomics rules and grids, such as ruler. It's something that you will only get thanks to physics engines computation. And so by using really physics control of the digital human model. Actually, to perform a specific posture in space, you have to apply some specific torques and efforts to joints. These torques, they are computed by the physics engine, and the torque to apply depend on the bone length and masses. They depend on the current posture, of course, of the digital human to reach. And they also depend on some external forces that are applied on the digital human model. These external forces, some example are the ground reaction force that you can see here on the right foot of the digital human model. They can be a hand payload. If you are handling a tool, then it will be more difficult to maintain a certain posture. And these external forces, they can also be represented by an exoskeleton assistance. So on the opposite of the hand payload, the exoskeleton assistance will provide you additional force to maintain a certain posture. The torque can be computed by solving the statics or dynamics equations of motions that I displayed here. The principle is quite the same as what I showed earlier with the QP problem, meaning that you want to minimize some certain amounts by having these statics or dynamics equations of motions as constraints. In the end, you will compute the torques, and the torques, they will give you some insights about what is the amount of efforts that has to be provided in order to reach and keep a certain posture. Okay. So the inputs are the external forces in blue here, and as output, we compute the joint efforts at each articulation. When you develop such simulation, the idea or the question you could have is, how can you define the external forces applied on the digital human? Well, the most basic way to do it is to define them manually with an application frame on a specific bone and a force direction and value. So that's what you can see here on the hand, here on the arm, okay? Here on the foot, there is an application frame and a force direction and value. And when you go on site, when you go and study a specific user with a motion capture hardware, you can also use some additional effort sensors in order to provide additional data on the efforts deployed by the user. So you could use insoles like these ones. You could use gloves. So it's not gloves used for motion capture, it's gloves used for effort capture. So you have some small dots here that can give you some inputs of the force deployed by the human hand. And also, when you use exoskeletons, sometimes the exoskeleton can give you the actual torque or force that is applied on the human arm. Here I give you a short video example about motion capture that we did with the Kinect Azure camera. And we also use insoles from Moticon. So those are insoles that you put inside your shoes. And these insoles give you data about the ground reaction force on the feet. So you have the center of pressure, and you also have the total amount of force deployed on each foot. So that's what you see on the right of the video. You see the center, the pressure center displayed here, and you also have the total amount of force. And depending on this input, we are able to compute correctly. So I will go back. We are able to compute correctly the efforts deployed at each articulation, like I would say here or here. Okay. Say here. Okay. Here I'm only resting on my right foot. My left foot has no pressure. The right foot has a pressure at the tip of my foot, and it's of a certain amount. And here, the red spheres you see on the human body, they represent the joint efforts on the ankle, on the knee, and on the hip. And as you see, the higher the sphere, the higher the effort. And quite logically, we have a higher effort on the right leg than on the left leg, because I'm resting on my right leg and not on my left leg. That's an example of how to use effort sensors and how to use them in order to compute the internal joint torques. Another example of efforts computations is a contribution of another PhD student who is able to compute joint torques for different workstations and different morphologies. That's what we will see on this video here. So the same principle is that the higher the sphere, the higher the torque, and based on the task that has to be performed, the talks are not the same. And also, depending on the human morphology, the talks are not the same either. For example, higher people need to bend further down, so they will have higher talks. On the opposite, lower people sometimes they need to bend more or less. So depending on all these parameters, the joint efforts are not the same. So that's an example. You can have more details on the publication article reference here. When we talk about effort, one big question is what is the acceptable value of efforts? And this is not an easy question. Actually, joint maximum torques or actually bone maximum force depend on people. Because you have people that have more muscles than others. They can deploy more force than others. And also, these maximum torques depend on the muscles and the body parts you're considering, meaning that you can deploy strong force with the shoulder, for example, or the elbow, but not necessarily with the wrist. The maximum amount of torques is different. I will not really go into details here, since it's really a complex question and it's not really the topic of the presentation today, but there are some notions that you might want to know and to study. It's the maximum voluntary effort, the MVE. It's the experimentally measured maximum amount of effort that people would want to deploy for a specific task. So it's if you want to apply force on a wall, what would be the maximum voluntary effort you would want to apply? Then you have the duty cycle, which is the total effort duration divided by cycle time, which is actually the percentage of time you spent applying an effort during your cycle time. And the important notion to understand is the maximum acceptable effort, which is a percentage of the MVE. This maximum acceptable effort, with this article, POD 2011, they state that this maximum acceptable effort is a percentage of the MVE, and it actually depends on the duty cycle. So the more time you spend applying effort, the less the maximum acceptable effort should be. So if you spend 0% time, or let's say 5% time applying effort, then the maximum acceptable effort should be around, I would say, 55% of the MVE. On the opposite, if you spend 70% time applying effort, then the maximum acceptable effort for a task should be only 10% of the MVE. When you know all this, then you can compute the maximum acceptable force by computing the percentage of the MVE. Okay. Well, this is one way to answer to the question of acceptable value of efforts. There are some others, but instead of a posture-related analysis in which we can have some standards like ruler, giving you some thresholds on angulations. For efforts evaluation, there is no real standard giving you some standard thresholds like this one. So it's quite complicated to analyze. One last point is about instead of analyzing internal joint torques, you would want to focus on muscle efforts rather than joint torques. So this is possible, but to do that, you need to use biomechanical models with muscles, okay? You cannot only rely on skeleton digital human model. These muscle efforts can be estimated thanks to this biomechanical modeling software, such as OpenSim, Anybody. You can also measure these muscle efforts thanks to sensors, specific sensors. And you have two main families of sensors to do that. You have the EMG, electromyography sensors. An example is from the biometrics company. This measures the electrical activity of the muscles. And the other family is MMG sensors, so mechanomyography sensors. One example is from the Moten company. And these sensors, they measure the mechanical activity of the muscles, so it measures the vibrations of the muscles. These are two different kinds of families. They can provide really precise results of the activity of the muscles and the percentage of the intensity of each muscle on which you place the sensors. But it requires really precise and dedicated analysis. It's quite complicated to analyze the results of these sensors. And another main topic of research is how do you define the acceptable level of muscle activity? And like the joint torques maximum effort, defining the acceptable level of muscle activity is not easy also. And I will not go into more details on this topic right now. Well, this is almost all for ergonomics evaluation. We saw how to use posture-related analysis, efforts analysis, and I gave some words about muscle analysis also. And now I will give you some use case and application that is quite related to the PeneloPe project also, because it's how do you use this ergonomics evaluation to study exoskeleton applications. Here I give you a schema from Charles Pontonnier that I like very much because it gives you different strategies on how to model the interaction between a digital human model and an exoskeleton. The idea is that you have your digital human model on one side. On the other side, you have your exoskeleton that is applying forces to the digital human model. And the question is, how do you model the interaction between the two systems? This is not an easy question, and you have different strategies to answer it. The most direct one is to actually model the exoskeleton as only torques and forces that are applied to the digital human model. That's the section on the left side here. So it's really easy to do, but it requires you to compute precisely what are the torques and forces applied on the digital human model. The second strategy is to model the exoskeleton as a kinematic chain that you see here. And this kinematic chain would be rigidly attached to the digital human model. That's the small lines you see here. These are rigid links between the exoskeleton and the digital human model. And by giving actuation forces on the exoskeleton, you are able to move the digital human model, and then you use your biomechanical simulation software to compute the joint torques on the digital human model, etc. The final strategy that is described here is that you will also model the exoskeleton as a kinematic chain. But instead of having rigid attach points between the exoskeleton and the digital human model, you would model the interaction only by using contact points between the two systems. This is really more complex to simulate, more complex to model. It's also more computationally expensive, and there are plenty of ongoing works on this topic. I will not focus on it, but it's just that you know some strategies about how to do that. In the following of the presentation, I will mainly focus on the way we did it in the PeneloPe project, which is the first strategy, which is by computing directly the resulting torques and forces to apply on the digital human model. Here is then a practical use case that we did for the PeneloPe project with the Comao-mate exoskeleton. It's an exoskeleton for the upper body, okay? Mostly assisting the arms, as you can see here. So the steps that we followed for evaluating some use cases with this exoskeleton, was first to model the exoskeleton kinematics and dynamics. That's what you see here. So there are plenty of revolute joints, prismatic joints also. Then the second step was to attach this exoskeleton to the digital human model. So here we use mainly rigid attach point and some springs to attach the exoskeleton to the digital human model. Then, based on the current posture and assistant level of the exoskeleton, we are able to compute the assistant force that should be applied by the exoskeleton to the digital human model. That's the red arrow you see here. And at the end, we use this as input. We use this as an external force applied to the digital human model. And in the end, we're able to compute all the digital human model joint torques, internal joint torques, that are necessary to maintain this posture. Here is the results in some short videos. We did plenty of tests depending on the human height and mass, the human posture, so different arm angles, different exoskeleton assistance, and different tool payloads. That's what you see here. And I will actually show it as a short demonstration just after. Or I could show it right now, actually. I will show it to you in live. I will open again my XREGO software. I will define my digital human model. Okay, let's have a basic height and mass again. I will add an exoskeleton here, I guess. Okay. Here I added an exoskeleton on my digital human model. So it's the mate exoskeleton, okay. I will go to simulation. Okay, the mannequin goes into standard T posture. I will move my mannequin into posture to show you. Okay, let's do it like that. I'm also moving the left arm. So as you see, as I move the virtual mannequin in space, the exoskeleton is also moving to match the current posture, okay? based on the current posture, I'm able to compute the actual force that is applied to the virtual arm here. I can change depending on the actual arm posture. I can change. So let's move this one a bit further so that it does not. You can see. Okay. So let's see it like that. I can change the assistance level of my exoskeleton. So here I have exoskeleton assistance 0, so it doesn't provide any assistance. If I provide the level assistance 1, I have some assistance force on the arm here, which is a bit low. If I give level assistance 8, then the assistance force is up here. And I can provide also some loads on the arms. Let's say I'm wearing a 3 kilo tool. Here, I see it. Let's move it like that. Okay. Okay. Here I see the effort that has to be applied on my virtual mannequin in real time, depending on the posture I'm getting, okay? Or that's an example, okay, of what we can simulate in real time by computing the joint torques. I will go back to the presentation. We have 10 minutes left. I will be short. Okay, you can see my presentation again. So here you have the videos here. What is interesting to see that we can also have on-site trials in our lab in which we can have the motion capture together with the exoskeleton simulation. Here are some screenshots of tests that we did with motion capture and exoskeleton simulation. We also performed some industrial on-site trials during the project by using motion capture sensors and also MMG sensors from the Moten company. And it was on the grinding activity. Here, there are some diagrams about the results we presented. If you want some more details, please feel free to go to this paper here that was published just at the end of last year. So we did studies with 4 different operators wearing the exoskeleton or not, and we wanted to study if the exoskeleton was of a good assistance or not. So check the paper if you want to know some more details and results. And here is a short video of what was provided as a deliverable of the PeneloPe project. That's mainly what I showed you as a demo just now. So we can move the assistance level of the exoskeleton, move the payload. This will automatically compute the joint efforts on the shoulder. We have generated some tables also to give some recommendations about what assistance level we should give depending on the operator height and weight, the arm's posture, the tool payload. And here are some video about live motion capture with the exoskeleton simulation. So together you have the ruler assessment, so for posture analysis, and you also have the efforts computation. This is some lab motion capture tests, and at the end you have some other analysis on site on the grinding activity. with the mate exoskeleton, and we can display the muscular activity in real time, depending on the current posture, depending on the current activity of the operator. So this was performed during the PeneloPe project, and this ends a bit the training session for today. As a short conclusion, we've seen some data about motion capture, hardware, software. We saw how to use it to control digital human models. We saw the differences between animation, traditional animation tools, and tools using physics engines. And in the end, we saw how to, based on this motion capture and digital human model, how to perform an ergonomics evaluation, either based on posture, based on efforts, and also could be based on muscles. And this gives a introduction of what is possible. And of course, thank you for your attention. If you have some questions, if you want to go into more details, you can contact me at this email address here. There are some references here that will be available later on as we share the presentation online. But of course, we have some time, I guess, for questions. So please feel free to ask them now. I would be happy to answer them.
I have one question about the complexity of the model, the human model you was presenting.
Yeah.
How much, for example, what is the main number of joints and the links you basically consider for the human model?
So for the one I'm demonstrating right now, we have 21 bones and we have 47 degrees of freedom.
Okay, so related question is basically on the same. So it's a really complex model, and in such case, understand when we are talking about physics, we have somehow the relationship in terms of mathematics somewhere behind. So coming back to this question, you have mentioned also very interesting tools, which is the physics based RL reinforcement learning algorithms. So is it, for example, a way that during those simulations you are able to generate the mathematical model of the human digital twin, or normally the representation is just like, because the QP normally have I think a series of equations which are interacting together. So with your insight, with the new physics based RL, is it possible to have those mathematical equations being updated, or is just basically how it looks normally in the simulations?
Well, for now, for what I know, the basic AI toolkits that are used to control physics-based characters, they would only provide the torques to apply to the physics-based character to move in space. They do not really have knowledge about the equations of motions. They do not have knowledge about explicit constraints. It's actually the physics engine which is responsible for it. So the main things these AI toolkits will give you are joint torques to apply to the virtual mannequin.
Okay. Okay, fine. And I don't know if you just give a bit of a overview of this MMG type of sensors from Moten. You have mentioned how basically if you just explain a little bit better, like how it measures the mechanical output of a muscle?
So these sensors are quite new, and we actually began to use them inside the PeneloPe project for this use case. And for now, we have also used them for other use cases with the other industrial partners. The principle is that they measure the vibration of the muscles, okay? So they would give you a certain amount of vibration, and depending on this amount, it would give you a certain percentage of muscle activity and muscle activity and intensity. So based on the maximum intensity of the muscle, okay? So it's quite the same as EMG sensors, but it's based
But
on
they are
vibration.
superficial, right? I mean, you are just going to attach it on the top of the muscle,
Exactly.
and it just have like a surface connector.
Yeah, it has to be on the skin, okay? So
Mhm.
as you see on the picture here, you have to put them and scotch them on the skin. But then the location doesn't need to be really precise. It just has to be on the muscle you want to listen. So that's the difference between MMG and EMG. EMG, you would have to peel the skin to add some lotion on the skin also, and the location of the electrodes would need to be really precise. So they're quite complex to use. With these MMG sensors, it's quite easier to use really in situation in the industry. That's my point of view. Uh,
Okay. Okay. Thank you very much, Vincent. Yeah,
okay,
for a nice presentation. Yes.
okay, thank you. Um, well, if there are other questions, I guess the time is up. Thank you everyone for attending.